Hey guys, this is my Lab 5 report. So this lab was pretty much just a redo of Lab 2. However, except instead of just observing the object on Earth, we were observing the object's motion across different planets of the solar system. Because this experiment was entirely computational, we're more just comparing the displacements the object traveled within the time frame. So the experiment showed some really interesting results that were expected, but nonetheless very exciting when visualized, especially the sun. The physics principles we use are pretty much just a redo of Lab 2. So we use the momentum principle to get the updated velocity and updated position function, and then we use kinematics for our position update as well when the object's in motion. The biggest difference here is just that in the kinematics and in this equation, the g is obviously going to be different on the different planets. So, as I said before, this lab was entirely computational and was done in GlowScript. The ball was theoretically dropped from a rest at a height of 2.3 meters on each planet, and then by using kinematics and GlowScript, the difference in displacement could be calculated, and the difference in gravitational forces could be seen. Since this code was reused from Experiment 2, it's assuming that the ball on Earth is being dropped and there's a floor at 2.3 meters. However, since this code is computational, it doesn't acknowledge that the floor is there. So we're more just comparing how far the object falls within the time frame of 0.7 seconds. And then these are the initial conditions. So it's at rest, so 0, and it was made to be at the origin, so the initial position is 0. And then the time is 0.7 seconds because that's how long it took to drop on Earth. And then the system is just the ball, and the surroundings would be the space around the ball or the planet that's exerting gravity. So pretty much, like as I said before, the code was reused from Lab 2. So obviously, we had to change the initial conditions. The G was obviously changed for each run through to the different results. And then since there was no drag force in this, we had to change that to 0. The rest was, again, pretty much a reuse from Lab 2 of implementing our updated position and updated velocity functions, as well as some of our kinematic equations. And then these were the planets we used within the experiment. So we had the Earth, which is obviously like our control, kind of, the Moon, Mars, Venus, Jupiter, and the Sun. So the results were very interesting. On the first graph, we have Earth. On the second, we have the Moon. The third is Mars. The fourth is Venus. The fifth is Jupiter. And the sixth is the Sun. So overall, they showed their expected values. Since the experiment was designed on Earth, obviously the ball on Earth fell 2.3 meters in 0.7 seconds. However, when you start messing with the acceleration due to gravity, the ball fell a shorter distance with planets that had a lower acceleration due to gravity. So the Mars and the Moon, I think the Moon was 1.6 and Mars had 3.7. Yeah. So they actually ended up falling a much smaller distance. So it only fell 0.37 meters on the Moon and 0.9 meters on Mars. On the other hand, it fell an even greater distance when the acceleration due to gravity was larger. So when we get into Jupiter, where the acceleration due to gravity is 24.5 meters a second squared, and then on the Sun it's 275. It actually fell 65 meters on the Sun in zero point 0.7 seconds, and then it fell 6 meters on Jupiter. And then finally, the last result was Venus. However, that was pretty much identical to Earth because Venus obviously is a sister planet to Earth. It has 8.87 as its acceleration due to gravity, which is almost 91% similar to the Earth's acceleration due to gravity. Since this experiment was entirely computational, there really wouldn't be any sources of error from any other forces acting because they weren't exclusively coded in. However, because it was computational, errors within the code could skew the results. So the discussion is, what if is essentially what the what if is asking is, this model heavily negates air resistance or any other forces. However, if you put them in, how would the results look? They would pretty much be almost identical, just slightly smaller. The force of gravity is a very strong in magnitude. So since the ball is a very small mass being dropped at a very small height, the forces acting on it wouldn't be that large in magnitude. And in fact, when you get into the larger forces of gravity like Jupiter and the Sun, it may not even make a difference at all when you calculate the displacement. And then obviously the what does it mean is you have the Earth and Venus have a very similar acceleration to gravity, almost 91%. How would this look if they were dropped at a much larger height? And then what does this indicate about the accelerations? So if you theoretically drop a ball from an infinite height and just let it go for 5 seconds, it falls a lot farther on Earth than Venus, despite their accelerations being like 91% similar. So it just kind of indicates that when you have an object, despite the accelerations due to gravity being so similar, when it's dropped over a very large distance, it will cause the displacements to be vastly different, potentially even exponentially different.